All right, this is section 2.5, complex zeros and the fundamental theorem of algebra. Finally, we're going to get into some real good, real interesting precalculus work. You should be able to factor polynomials with real coefficients using factors with complex coefficients by the time you're done with this section. Remember, when we're talking about complex numbers, we're talking about numbers that are in the form a plus bi. So what that means to you is the number has a real part and has an imaginary part. That's a complex number. Sometimes the a is 0, sometimes the b is 0. So when we talk about complex numbers, we're talking about numbers that could be real, could be imaginary, could be both. So keep that in mind. The fundamental theorem of algebra is a polynomial function of degree n has n complex zeros, whether they're real or non-real. Some of these zeros may be repeated. So what that means to you is whatever the degree is of the polynomial, it has that many zeros. Well, what the linear factorization theorem says is if f of x is a polynomial function of a degree greater than 0, then that function has precisely n linear factors, where a is a leading coefficient, and each of these z's with a different subscript are the complex zeros. So if you think about it, what we just said is basically the fundamental theorem of algebra again. If a polynomial function of degree n has n complex zeros, well, that's the same as saying it's going to have n number of factors. Remember, when we're talking about factors, we're talking about zeros at the same time. So basically all this is saying is you can break up any polynomial function into, if it's an nth degree polynomial function, you can break it up into n linear factors, some of which may be repeated, multiplied by some leading coefficient a. And again, what's written up here on the board now is just repeating what we've been talking about, connecting them all together. X equals k is a solution or root of the equation f of x equals 0. Another way to say that is k is a zero of the function, or x minus k is a factor of f of x. Those are all talking about the same type of thing. So in this first example, we're bringing back work with imaginary numbers. Write the polynomial function in standard form. Identify the zeros and identify the x-intercepts of its graph. So if we write this in standard form, we're basically just foiling out. But remember, what's really nice about this is it's the exact same factor, only there's one of them's minus and one of them's plus. We call these conjugates. When you're multiplying conjugates, the middle terms cancel out. So we know this is going to equal the x squared minus the 3i squared. And that's going to equal x squared minus 9 times I squared, which is going to equal x squared plus 9. Now, That would be writing the function in standard form. Identify the zeros. Well, what would the zeros be? They would be, well, let me remove this summary here for you. That way, if you're copying down notes, you can copy that or copy what I'm saying. We've just written down the function. The two zeros would be 3i, because if I plugged in a 3i here, I'd get 0. If I plugged in a negative 3i here, I'd get 0. Same concept as before. So 3i and negative 3i are the zeros. Because the zeros are not real, the graph of f has no x-intercepts. And that should make sense to you, because where is this graph going to be located and what is it going to look like? It's a parabola opening up, located 9 units above the origin. So of course it would not have any x-intercepts. Now here's a real important note. The complex conjugate zeros. Suppose that f of x is a polynomial function with real coefficients, like normal. If a and b are real numbers, and b is not equal to 0, and a plus bi is a 0 of f of x, then its complex conjugate a minus bi is also a 0 of f of x. So basically what that's saying is, if you have a 0 that includes an imaginary number, then its complex conjugate must also be a 0. So if I told you that 3 minus I was a 0, then 3 plus I must also be a 0. Basically, a way you can think of that is that zeros that have imaginary numbers, they always come in pairs. You'll never have an odd number of complex conjugates, and they'll always have, you'll never have an odd number of zeros that include imaginary numbers. You will always have the complex 0 along with its conjugate. So here's an example of finding a polynomial form, or excuse me, finding a polynomial from given zeros. So I want you to write the polynomial function of minimum degree in standard form with real coefficients whose zeros include negative 3, 3 minus I, 2 plus 5i. So when we're talking about of minimum degree, you're basically, the zeros that you find here are only going to be used once, unless stated otherwise. So what I can tell right away is, if I have negative 3 for a 0, well, that tells me that I'm going to have x plus 3 as a factor. If I have 3 minus I as a 0, well, then I also must have 3 plus I. So this tells me I have 2 zeros here. If I have 2 plus 5i as a 0, I must also have 2 minus 5i. So this is actually telling me about 2 zeros. How many zeros am I talking now? 5. 1, 2, 3, 4, 5. So I'm just going to write that out. What I just revealed is basically what I just said. So if I write this out, I would write x minus a negative 3, which is x plus 3, and I would write x minus 3 minus I, and x minus 3 plus I, x minus 2 plus 5i, and x minus 2 plus 5i, or 2 minus 5i and 2 plus 5i. So this next step, all I'm going to do is I'm basically going to rearrange where the parentheses are inside of these brackets. I'm going to rearrange them so that you can see a pair of conjugates being multiplied together. Let me reveal this and show you what I mean. All I've done, since we're just subtracting two things here, I don't even need a set of parentheses there. But I'm basically removing these parentheses and just putting them now around the x minus 3 and x minus 3. That's what I've done here. I haven't written anything new. I've just changed where the parentheses have gone. I've done that here also. That way, you can basically think of this as the first term and the I as the second term. Think of this as the first term and the I as the second term. Can you see how these two together are a set of conjugates being multiplied together? These are also a set of conjugates being multiplied together. That's going to make it a little bit easier to multiply them out. What I'm going to do first is I'm basically just going to focus on multiplying these together first. I'm going to do a little side work, if you will. Since these are conjugates being multiplied together, remember the middle terms end up canceling out. All I need to do then is square the first term minus the square of the second term, as indicated here. Well, you know x minus 3 squared is x squared minus 6x plus 9, and you know I squared is negative 1. Combine those together, and you've got x squared, x squared minus 6x plus 10. I'm going to do the same exact type of work over here. I'm going to combine these two, since these are conjugates of each other, in the same exact fashion. So see if you can do that in the same way right now. Is this what you got? Now, it's going to be just basic algebra, and you're not even dealing with complex numbers anymore. So this next statement, I'm going to bring down everything we found. X plus 3 times x squared minus 6x plus 10 times x squared minus 4x plus 29. Now you start multiplying those out. So what I would do next is I would multiply x plus 3 times x squared minus 6x plus 10. The way I do it is I multiply all three terms here by x first, then all three terms by the 3. So I would get x cubed minus 6x squared plus 10, x. And then right below that, I would write in the 3 times each of those, and I'd line those up in the appropriate columns. So I'd have a plus 3x squared minus 18x plus 30. When you line them up, it's real easy to combine your like terms. You have an x cubed minus 3x squared minus 8x plus 30. Then I'd bring down what I haven't multiplied by yet. And now I would do the same exact thing again. So I'll do this next step a little bit more quickly here. And this time I would multiply everything in the first polynomial by each term in the second polynomial one at a time, leaving everything in the appropriate columns, just like last time. So here goes. I'm going to take x squared times everything first. And now I'm going to take everything times negative 4x. And then finally everything times 29. And then once you do that, you just add up each column, and you're pretty much done. That's your final answer. Well, that's fun. It's too bad that we don't have time to go through a whole bunch of problems like that, because that is some good work. Really good work. Hopefully you don't get discouraged when you have a lot of work to show and you actually are proud of that, because it's really good stuff. The last note that you can take here is that every polynomial function with real coefficients can be written as a product of linear factors and irreducible quadratic factors, each with real coefficients. That's what we're going to go through an example of right now. You're going to use the function f of x equals 3x to the fifth plus x to the fourth minus 24x cubed minus 8x squared minus 27x minus 9. And we're going to rewrite that as a product of linear and irreducible quadratic factors. The irreducible quadratic factors are basically quadratic polynomials that you cannot reduce because you would get imaginary or complex numbers with imaginary parts as your solutions. If you took the time to graph this polynomial function, you would find that x equals negative 1/3 is a 0. Since that's a 0, we can use synthetic division to factor that out. So this is just your basic synthetic division. Negative 1/3 is a 0 that I found on my grapher. Now I'm just writing out the coefficients. And I'll give you a second to try to do that. Alright, that was probably enough time, so I'll go ahead and do that now also. And we got a 0 here, so that means that the negative 1/3 was a 0. Perfect. That's what we wanted. That's what we hoped for. What do these numbers here mean? Well, that means after I factored out an x plus 1/3, I ended up with, since we started with a 5th degree polynomial, I ended up with 3x to the 4th, didn't have an x cubed, minus 24x squared, didn't have to the first power, so minus 27. Now what I would do at this point is, since each term that's left is divisible by 3 or has a factor of 3, I would factor that out. So I would have a 3 times x plus 1/3 whoops. Oh, that really did it. That was like a jumbo size eraser. We didn't want that. We just wanted a little half eraser there. So where was I? Factored out a 3, now I have x to the 4th minus 8x squared minus 9. Wonderful. I've got a quartic or a 4th degree polynomial. There's something that you should notice about it. What you should notice about it is it's in the same form as your quadratic. You can factor a quartic that's set up where you have the 4th degree, 2nd degree, and constant, just like you can factor your quadratic. So you're still going to ask yourself, what do I multiply to get x to the 4th? That's going to be, set it up like this, x squared times x squared. What do I have to multiply to get 9, or negative 9, and what I have to add together to get negative 8? Well, you would tell yourself that you're going to have to subtract 9 and add 1. That's what this would factor into. Now once you do that, there's one of these quadratics you can factor down again. Obviously, it's the x squared minus 9. That can be rewritten as x minus 3 times x plus 3. There we've simplified down what we had in the way that we were requested, a product of linear and irreducible quadratic factors. These three here are linear factors. This is an irreducible quadratic. That was some good stuff. Thanks. And that's it. That's the end of the lesson. I don't know why you're still hanging around. Oh, you're waiting for a math joke probably. Well, since it's Halloween, I guess I can give you one. How about what do you get if you divide the circumference of a jack-o'-lantern by its diameter? Who said it? Anybody say it? Pumpkin pie? Get it? Yeah, that was a good one. It's a good one. Tell your friends.